by partial fractions, I'm gonna give you the rules and then we are gonna solve some problems. Partial fractions is f over g. So what would you do is first of all look at g and try to factor g, okay, if you can. Alright, and the rule says let's take the g which is in the denominator of the rational function f over g is our rational function. Consider the denominator g. Let's take a linear factor from it, x minus r, and let's say x minus r has a power m. Okay, let's say m is the highest power. Then what you're going to do, you're going to take that and then assign the sum of the m partial fractions like that, and we are going to have a1, a2, am. These are constants, and x minus r plus a2 x minus r squared plus da 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 until am x minus r to the m, till you exhaust the mth power. So we are going to do this for each distinct linear factor of g. Okay, that's how we would do. And let's say g might have irreducible quadratic factor like x squared plus px plus q, which is irreducible. You won't be able to factor it out into linear factors. In other words, x squared plus px r to q has no real roots. Okay, if that's the case, and let's say n is the highest power of this factor, then what you're going to do, similar thing, but on top, instead of a constant, on top you have the linear expression b1x plus c1, b2x plus c2, blah blah. You're going to do this until you exhaust the power. You are adding them up. Okay, we are going to do this for each distinct quadratic factor of g that is irreducible. Okay, and now set the original function f over g equal to the sum of all these partial fractions. And then we are going to clear the resulting equation of fractions, which means equate the denominators, etc. And at the end, we are going to equate the coefficients of corresponding powers of x and solve the resulting equations for the undetermined coefficients. These are the steps. Okay. Okay, these are again lecture notes from fall 2019, integration of rational functions by partial fractions. What's a partial fraction? These are partial fractions, as you will see. 2 over x minus 1, 1 over x plus 2. Okay, this is the rational function. This rational function, the denominator can be factored out into two factors, x plus 2 and x minus 1. Alright, and then we want to express this as sum or differences of partial fractions like that. How would you do? There's a method, and we just described roughly how to do that. Okay, I just want you to understand what's a partial fraction, what's a rational function, etc. Now, in our class, the questions are going to be like that. You would ask to find the integral of a rational function like this: x plus 5 over x squared plus x minus 2. I want to remind students who forget about rational function. Rational function is a function written as a ratio of two polynomials. So x plus 5 is a polynomial, x squared plus x minus 2 is a polynomial. If you have an expression written as a ratio of two polynomials, it's called a rational function. Okay, so in this example, actually we assume that we know what this is equal to in terms of rational fractions, partial fractions. Okay, partial fractions, because this is equal to this. Definitely that's true. If you equate the denominators, you get this back. Writing the partial fraction expression is very useful. This example shows because this is equal to then this minus this. This integral is easy to integrate, we call it I. This integral is easy to integrate, we call it J. And then I is, of course, you do the substitution here. U is equal to x minus 1, dx is equal to du. So integral, instead of x minus 1, I put u now, substitution. Dx is du, I put du. Now I just concentrate on this. I know integral 1 over u is natural log of absolute value of u. Keep the 2 in the front plus c. Okay? And then rewrite or substitute what u is in terms of x, and 2 times natural log of absolute value of x minus 1 plus c is the answer. Next thing was j. Integral 1 over x plus 2 dx. We use substitution again. U is x plus 2, dx is du. And du over u, this is natural log of absolute value of u plus c. Write back in what u is. U is x plus 2, and this is the final answer. So we found I and j. So the chi, which is the given integral, is equal to I minus j. So the answers were 2 ln absolute value of x minus 1 minus ln absolute value of x plus 2 plus c. Okay. So how do we get this? The question is, how would you write? What's the method to write this in terms of partial fractions? Actually, we just said it at the beginning, roughly, but I'm going to show you how you do that. First thing, you're going to take this partial irrational function, factor out the denominator into linear factors, okay, and you put, for each linear factor, you just write a over x minus 1 and b over x plus 2. See, the linear factors in here, they don't have powers. At the beginning, we said that if they have powers, you're going to write a1 over x minus 1, a2 over x minus 1 squared, etc. But since the powers are 1, you don't have to do that. You just use just a over x minus 1 plus b over x plus 2. We put a star next to it, and then equate the denominators on the right. You equate the denominators, you do that. Ignore all the denominators, because once the denominators are the same, you just look at the numerators. X plus 5 is equal to a times x plus 2 plus b times x minus 1. You can distribute this over, and you gather the like terms. X is a like term, common term for a and b, and then 2a minus b is just constant term. And look, now compare this with the right hand side. What's the power, what's the coefficient of x? It's 1. So the coefficient of x on the right has to be 1 too. So a plus 1 has to be 1. And what's the constant term here? It is 5. What's the constant term here? 2a minus 5 minus b. This is 5. So I got a system of equations here. Then I solve the system of equations and find a solution. I add them up. These are going to cancel. I have 3a is equal to 6, a is equal to 2. Once a is equal to 2, b is equal to negative 1. So I got a and b, and I go back up here and put a and b here. A is was 2. Was it 2? Let's see. Was it 2? A was what? A is 2, b is negative 1. A is 2, b is negative 1. A is 2, b is negative 1. Let's go up here. A is 2, b is negative 1. So we got it right. Okay, that's how you would do that. That's what we got that. Okay. So let's do the next 3, I think 3 or 5, 6 examples. Yeah, 6 examples. The first example. So I divided into cases. I call them cases. They are showing different cases: case 0, case 1, case 2, case 3, case 4, and then rationalizing substitution you can consider as case 5. Let's look at the first example. The first example is this. This is polynomial over polynomial. This is a rational function. When you have a rational function where the polynomial has a bigger degree in the numerator than the denominator, we call it case 0. What would you do is, you're going to do the long division. X cubed plus x divided by x minus 1. you divide by it. How many times? X squared times this, x squared minus 1 is negative x squared times x cubed, take the difference, this minus this is 0, this plus x squared, so I have x squared plus x, because there's minus, it makes it plus. X squared plus x, how many times do we have? X many times. X times x is x squared, x times negative 1 is negative x, take the difference, you get 0 here, you get 2x here. How many times do we have? We have 2 times x minus 2, take the difference, and we have 2 is the remainder, okay? And okay, so I'm just telling you, we imitated this. Look, next we are going to write this rational function as sum of two functions as follows. 41 divided by 2 is 20, and remainder is, how would you write 41 over 2? You're going to write 20 plus 1 over 2. We are going to imitate this, and we are going to write x cubed plus x over x minus 1 as, this is what we got here in the division, okay? And then division, yeah, where is it? Okay, and plus the remainder over the quotient x minus 1. So this expression from now on is just this plus this. Very good. It's simpler now. This integral is easy. It's a polynomial. This integral is easy, also natural log, and we finish it off. Don't forget to put c. And case 1, so the degrees are, this degree is less than this, so this case 1 is when you have the polynomial over polynomial and the denominator has linear factors. Alright, so in this case we have linear factors, x, 2x minus 1, x plus 2 if you factor it out. Alright, so, and okay, and you just say a over x, b over 2x minus 1, c over x plus 2. That's what you write. And we want to find a, b, c. As I told you before, you equate the denominators, you ignore the denominators afterwards, you gather the like terms, as we did here, you gather the like terms, x squared, x, and the constant term, and compare with the left hand side. The coefficient of x squared is 1, and the coefficient of x squared is 2, so this has to be 1, and the constant term is negative 1. So you write them in here. Negative 2a is negative 1, 2a plus b plus 2c, which is this, is 1, and then this is 2. You write it in. From here you get a is 1 over 2. Once a is 1 over 2, you put it in, okay? Then you get b is equal to, you put 1 over 2, 2 times 1 over 2 is 1, 1's are going to cancel, b becomes negative 2c. Take this b equals to negative 2c, put it in here, and you get c to be negative 1 over 10, and b is equal to 1 over 5, and you are good to go. You found a, b, c. That's what we wanted. Then this expression is equal to a over x plus b over c, b over this plus c over this. We found a, b, c. And this is 1 over 2 ln x absolute value. This is 1 over 5. 1 over 2 comes from the coefficient of x, ln 2x minus 1, plus negative 1 over 10 ln x plus 2 plus a big C. Don't forget C. That's the final answer down here.